Okay, so welcome back. Last time, we have only found the domain of the function y equals x to the x power, and we actually spent quite a lot of time to talk about the difference between range and the codomain of a function, so that we don't actually get confused between the two ideas, as well as understanding why when we say having the condition here gives out the codomain of the function, which leads us to define what the domain is. So now we're going to continue and finish the rest of the problems. So how are we supposed to find the relative maximum and relative minimum, or known as the what's this called? Relative extrema. For some people, they just simply call it the local extrema, because again, we're now looking the local parts of the graph instead of the whole graph. Okay, and as we know, to find out the relative extrema of a function, if we have a nice function such as a parabola, of course we can just simply use the graphs, and again, we can always use the graphs to help us finding the relative extrema of the function. But as we said, we're trying not to use the graph, but use calculus techniques to help us finding it. And for the graphing part, we'll leave it at the end and trying to use that to try to verify our answers. So without using a graph, what's the best way? If it's a parabola, everyone knows that there's only one relative extremum, which is at the vertex. But if the function is something in higher power, or something that's not even a polynomial, then we have to use the derivative to help us. In fact, we know that the first derivative will help us in getting the relative extrema. So let's see. Given the function y equals x to the x power, if we're going to take the first derivative, which is dy over dx, or y prime, we are going to get, and again, I'll just write out the answer. How to get that, we already have another video in the past that actually showed how to get the first derivative of x to x power. So you can go back and find it out. So we're going to get x to x power times the quantity 1 plus ln of x. Then to find out the relative extrema, of course, we need to set this equal to 0. And again, we know that the possible locations for relative extrema locates when the first derivative is equal to 0. In other words, when the point has 0 tangent slope. So let's see. Since we know the domain of this function is all positive numbers, we already claimed that the function itself, x to the x power, is always positive. So in order to satisfy the first derivative equaling to 0, we have to have at least one of the factors equal to 0. Meaning that if x to x power is not equal to 0, the only way to get it equal to 0 is the second term, 1 plus ln of x equals 0. So if we solve for x, we find out that x equals 1 over e. Good. So now we know the location of the relative extrema. We next need to determine whether it's a relative maximum or relative minimum. But before that, since we are trying to find the points, we also need to know the output, or the y value of it. So how do we do that? Well, since we know the x value, we just substitute back into our original function. So we get y equals 1 over e, all raised to 1 over e power, which is equal to 1 over the e root of e. Good. keep in mind this is one of the points. Next, we can actually solve it in two different ways. One way, we can just make a table like this, and we're going to label a few things: the x value, and then the first derivative at that x value, and also the y value, or the output, which means we're going to find the locations. So what we're going to do is we're going to label all the points when the first derivative is equal to 0, and then for everything in between we'll just put dots here to represent that it includes everything else. For example, we know that x has to be positive, so for everything before the 1 over e, we're including everything from 0 to 1 over e, not including the two endpoints. So we're going to get similar things, such as for the 3 dots after 1 over e, it includes everything. So how does it help us? We can now choose any values inside of the 3 dots, inside of the open interval, and then to use the values inside of the open intervals, helping us getting the sign of the first derivative. So first, we already know that at 1 over e, the first derivative is equal to 0. And of course we have the y value, but here I'm going to leave it as it is, because the main point is finding out whether it is a maximum or minimum. Then, now we need to figure out the sign when x is less than 1 over e, as well as x is greater than 1 over e. So let's say when x is greater than 1 over e, we can just pick something such as 1, and then substitute back into our first derivative equation, which of course gives us, here is a positive value, times 1 plus ln of 1, where ln of 1 is just 0. So we have 1 plus 0, which is 1, is also positive, and we end up with positive value. Similarly, if we choose something that is less than 1 over e, such as let's say 1 over 10, we still end up with x over x, x to x power is greater than 0. But for the second part, we have ln of 1 over 10, which is negative, and in fact it is less than -1. And then plus 1 will end up with negative still. So we have a positive value times a negative value, meaning that the whole product is still negative. How is it going to help us? Well, this is going to show us that the graph looks like this. It's gonna first go down before we hit 1 over e, and then after the point, it's gonna go back up. Meaning, graphically, we will have a relative minimum here, or known as the local minimum, because for all the points around the 1 over e, the y value will always be greater than or equal to 1 over e. So now we have determined that when x equals 1 over e, that point is the relative minimum of the graph. And that is it. We don't have any relative maximum, because there's only one location here. So now we can just fill out our answer. Is there any relative maximum? From here, we know that it does not exist, D and E. Is there any relative minimum? Yes, we found it. It's 1 over e, comma, y value, 1 over the e root of e. Good. So another way of determining whether the point is a relative maximum or relative minimum is we can also take the second derivative of the graph, so that we can actually see what sign the second derivative is. If we have a positive sign, we actually get concave up like this. And if we end up with a negative sign for the second derivative, we actually will have concave down, or some people call it convex. So that we know that the graph around that point is either turning up or like a regular U shape, or it's gonna turn down like a upside down U shape. And then we can just combine it with the results that we have to tell whether that point is either going up or going down. Okay, and also known whether it's the relative maximum or relative minimum. So in this case, we can just combine together and seeing that this is going to end up with like with here relative minimum. Good. So now we're going to move on to the next two, the absolute maximum, absolute minimum, aka the global maximum and global minimum. Because now when we look at the graph of the function, we're looking at the entire graph, meaning that we're no longer looking a partial region of the function. We're going to compare all the x's in the domain and to determine where's the highest point or the lowest point in the graph. So if we look at here, we see that this in our table, the x values is starting from somewhere not too low, and then it's actually decreasing. So it's getting lower and lower until we hit x equals 1 over e. And then after that, it starts going back up, and it continuously going back up without any breakup or any jump discontinuity. Meaning, in this case, we can already determine what the absolute minimum of the graph is, because this is the lowest point of the whole graph. So by taking the first derivative, we actually end up with finding the relative minimum, relative maximum, as well as the absolute maximum in this case. So when, since that is the lowest point that we can get as we compare all the points, we will say that the absolute minimum of this graph will be 1 over e, comma, 1 over the e root of e. Now, we still didn't do the absolute maximum. So how do we do it? We need to go back to the old rules that we have learned in pre-calculus, which says for a continuous function, the absolute extrema can only contain in two different possible ways. Number one, it is a relative extremum. Number two, it's the endpoints. So now we need to consider our endpoints. But of course, since this is an open interval, not a closed interval, we cannot include 0 and infinity. But how do we do it? We can now try to assume that when we're approaching to those limits, meaning we're going to take x approaching to 0, and when x approaching to positive infinity, and consider how the results end up with. So when x approaches to 0 for the function x to the x power, well, in fact, this is we need to use some kind of graph to explain how we actually get the value, but we will actually end up with 1. So the way of thinking of it is we can rewrite the base into base e, but to do that, we are now going to end up with ln of x, because we changed the base from x to e. And then don't forget, we're still raising it to the x power outside. So this is going to give us e raised it to the product of the two exponents, x to the ln of x power. And you might ask, right now we have x is approaching 0, but ln of x, or when ln of 0 is approaching to negative infinity, what can we do? We have 0 times negative infinity. Which one is going to dominate? So here, of course, we assume we are in calculus 1, So we don't know what so-called L'Hopital's rule yet. Don't try to use it, and of course, if you use it, you'll be able to get the same answer anyway. But keep in mind, without the L'Hopital's rule, we have a rule of the order of the functions, meaning that which one is going to dominate another one when we try to take the limit. So, in other words, when we have the two functions, one is a polynomial, the other one is a logarithm. The speed of the logarithm is always slower than the speed of the polynomial, meaning that if one is going to 0 and the other one is approaching to negative or positive infinity, right here, the positive or negative infinity is not growing as fast as the 0 in the polynomial, so that we will actually end up with 0. And again, you may actually wonder why this has to be the case, but it is not easy to explain until we have learned the L'Hopital's rule or use graphical examples to show why it is true. So just follow just follow this idea, and we should be able to get the results right now. So in this case, this term is going to approach to 0, and of course e is a continuous function. We can just throw in the limit into our exponents. And again, why is this true? This is also based on the theorems, and how to reprove it is something that's beyond calculus, which you need to know in real analysis class. But that is that's over our topic, so we're going to skip it right here. If you're interested of the proof behind the theorems or the reasoning, you can just go to look it up by yourself. Or if I have time, I might try to make videos and talk about those. But anyway, since now we're saying that as x approaching to 0, the x term, the polynomial, is going to dominate the whole product. So this is going to give us 0, meaning we end up with e raised to the 0 power, and that is just by definition is equal to 1. Good. So we know that when x is approaching to 0, this whole thing is gonna approach to 1. Now, how about when x is approaching to infinity? This is of course a lot easier, because clearly x is approaching to infinity, implying that x is greater than 1. That means this is already strictly greater than x itself. And again, because we're raising it to x power, or this is equivalently, or let me put it this way, it is greater than x to the first power, because x is greater than positive 1, and when we have a base that is bigger than 1 and raise it to some power bigger than 1, the end result will definitely be greater than the just the value itself, the x. And now we're going to see what happened. Even when we're considering the the polynomial function or the linear function x, when x approaching to infinity, we end up with positive infinity, meaning that this, let me write this, tend to positive infinity, meaning that if we consider the original function x to the x power, and suppose that x is approaching infinity, this function is also approaching to positive infinity. So this is going to approach to positive infinity. So now we actually can see how the two ends of the function goes. So back to the question, what is the absolute maximum? Now we just need to compare between the three values that we found. And we see that the maximum, what's so-called the maximum, is positive infinity. But of course, this is not a number. Infinity is just a notation of explaining the idea that all numbers cannot satisfy, and it will actually go beyond any number that we can choose. Therefore, since there is no bound here, or we cannot choose any number that gives us a bound, there is no absolute maximum. So this does not exist. Great. And again, the idea of infinity is saying that we cannot set a number as a boundary such that all the numbers or all the y values that we have in the function has to be no bigger than the boundary that we set. Meaning, in this case, no matter what number we choose, we can always find out some positive, some y value in this function that goes beyond the number that we choose. And that's the idea of infinity. So now we can finish up our problem. Using the table here, we can now determine what the range is. Since there's no absolute maximum, it means that the range here is going to approaching to infinity. So here we have the right hand side, or there's no right endpoint. The right side will be positive infinity. Now for the left side, what can we do? Of course, use the absolute minimum, because we know that this is a continuous function inside the domain. There is no jump discontinuity. There is no breakup. So in this case, as we consider the function is always continuous, meaning that we will not need to find out if there is any gaps between the interval that's not been including. So to figure it out, we just need to look at the absolute minimum. And here we have the absolute minimum, which is 1 over the e root of e. And keep in mind, when we talk about a range is referring to the dependent variable. So in this case, it will be our y value. So if we try to use the results that we found, we just need to use the y value of those results to do the comparison, and then we'll be able to get the range of the function. Now, last but not least, should we include this point here? Yes, because this point is actually inside of the function, right? The point 1 over e, comma 1 over e root of e is actually one of the points in the function, meaning that this point actually, this value actually exists in the function. So we definitely need to include it. How do we get it? Well, since we need to include the value, we need to put a bracket. So here, we need to be careful that when we use the notations here, this is a set notation, and it only contains one variable with one variable, meaning that this, we're only considering the y value, and this here is what we call an interval. An interval, okay, where these two here are actually the point on the plane, or the graph. So just be careful that this the notations actually look similar to an interval notation, but these two right here are actually the point on the graph, but not an interval like here. So that's it. Now, last, we're going to look at the graph of the function y equals x over x, so that we are going to try to confirm our answers are correct. So how will it look like? It actually looks something like this. Here is the y, here is the x, and then we're going to use the points that we found to help us in graphing the function. So we have 1 here, we also have 1 here. There's a reason, because we'll see why I'll label this. We also need 1 over e for x value, where the y value will be 1 over the e root of e, like this. So one point that we found is, of course, 1 over e comma 1 over e root of e, which is the minimum of the graph. And then when x is approaching to 0, y is approaching to 1. So we are going to make a circle, an open circle on on the coordinates 0, 1. And then here is the reason why I labeled x equals 1, because that's one of the easiest point to find on the function. When x equals 1, y is equal to 1 to first power, which is equal to 1. So we actually will end up something right here. And in fact, now we can actually connect the points to give out the graph of the function. So this right here is relative minimum, so we get something like this, and then it's going to go up like this on both sides. So this is the graph of the function x to x power. So we'll be able to get that here, the relative minimum, as well as the absolute minimum, because if we look at it, no matter globally or locally, that's the lowest point of the graph. Good. And then there's no relative maximum, because we don't see any points locally that has no points higher than it. We can always find points going higher. And you might actually argue, how about this point? Isn't this the highest point? Unfortunately, we cannot say that, because we cannot have x equals 0. And we can only have x is approaching to 0, but we cannot choose any positive values either, because no matter what positive value we choose, we can just have that value, and then the y value the y value will end up with higher than what we chose. So for example, if we are going to choose something like, let's say 1 over 100, okay, then if x equals 1 over 100, then we will have y equals x to x power, which is 100, or let me rewrite as 10 to the negative second power. So we end up with 10 to the negative second power, raise it to x, which is 1 over 100. This is 10 to the negative 1 over 50 power. But if we try to half it, or try to take 1/10 of it, we will actually get the y value that's even closer to 1, or greater than the y value that we just had for x equals 1 over 100. So we will actually end up with y equals 10 to the negative third power, raise it to 1 over 1000, or we can just choose 1 over 10,000, so that it's easier to calculate. So in this case, we will get 10 to the negative 1 over 2500 power. So this value is definitely greater than this and is even closer to 1. And we can continue playing this game and it will never end. And therefore, we cannot claim that there's a relative maximum on the left-hand side of the graph either. Okay, so we confirm that. And for absolute maximum, we see that it does not exist either, because as x approaching to infinity, it's going to blow up as well. Good. And then the range, again, the range is just the last thing we're going to check, which is taking this part here. Here is the lowest point we can have, and we're going to take everything above. As the function is continuous, we're not going to have any value or any y value in the red part that is not included. Good. And then of course the domain is the easiest to check, because we're going to look horizontally this time. We start off at x equals 0, but not including it, and we see that the function is continuous, meaning that there is no any x value, positive x values. We actually get skipped. Good. So this is how the application of derivative, or some part of calculus that we can actually use in some problems, or doesn't have to be a real life problem, but at least we're not just simply doing derivative for no reason. We can see how the idea of derivative helps us to understanding or analyzing the graph of a function, or the function itself, especially when we don't even know the shape of the graph, or if we're not allowed to use the graph, helping us to find some of the details. Okay, so that's it for this video, and this short series is not over yet. For the next video, we're going to look at another function, and it's a function that is a lot easier to find out all these details. And in fact, it will be a function that even when we don't have the knowledge of calculus, we'll be able to analyze the function. Okay, so if you enjoyed this video, don't forget to like and subscribe to my channel so that you can find more of my other videos. Also, if you have any thoughts, you can actually leave your comments below, or if you have any questions, you can also leave your comments below. I will see you guys in the next video.